So we're back. So here's a second example. So this is somebody on a swing. So we have the swing. So let's picture the swing like this. There's the vertical direction. Here's the section of the circle that we're going to go through. It's a 2 kilogram ball. So let's do the 2 kilogram ball. Is attached to a branch. So here's the branch. By a rope that is 4 meters long, so that's going to be 4 meters. And the ball swung in an arc, forming a pendulum, so it's going to go backwards and forwards like swings do. The speed of the ball at its lowest point, oh, that's interesting. So now I'm down here, and the speed of the ball at its lowest point is 7 meters per second. And then what is the tension in the rope at its lowest point? So I really need to visualize the lowest point. And I see that the tension in the rope is pointing upwards. And that's what I want to find out. So I know that my mass is equal to 2 kilograms. And I know my V is equal to 7 meters per second. And I know my R is equal to 4 meters. And T is what I want to find. I know it's circular motion. I know it's non-uniform circular motion. But what I know is that I'm talking about the instant when I'm vertical. So I say, well, the sum of the forces vertical equal. Am I in equilibrium vertically? What do you think? Am I in equilibrium vertically? If you think yes, click A. A, you are in equilibrium vertically. B, you're not in equilibrium vertically. So A, you are in equilibrium vertically, or B, you're not in equilibrium vertically. So A equivert, B not equivert. Let's see what people are saying. What's your visualization telling you? Any more? You can put down C, D, or E if you're just not going to do it. You know. Give it just a couple more seconds and then. Okay, stop. Yeah, it's not unanimity. There's some issue. And somebody on B. Let's pick on that small group. B. Why did you say it was not in equilibrium? Who's going to volunteer and give me the answer? Yeah.
Acceleration changes.
Well, no. It's not. You've gone through it. Anybody else? He's like 90% there. He's just gone through it. There is an acceleration. Doesn't have to change. There is an acceleration. Because when you think about it, it's going in a circle. So there is an acceleration. And so I cannot be in equilibrium. Okay? I'm going in a circle. There must be an acceleration. Now, I've not got all my forces down. Of course, I have Fg, which equals 20 newtons. So now I focus on this bit. And I say the sum of the forces vertically equals ma, because there is an acceleration. And it's mac, because there's an acceleration centripetal, which equals mv squared over r. And then I look at my diagram. And I say plus t added to minus 20. The weight is negative, the tension is upwards, the way I've drawn it. And that equals my mass, which is 2, times v squared, which is what I want, which I have, which is 7 squared over r, which is 4. So T is equal to 49 over 2, which is 24.5 plus 20. So T is equal to 4.5 plus 4.5 newtons. So again, what was my approach? I drew a decent diagram. I applied Newton's second law because there was an acceleration, this time vertically. I recognized that the acceleration was a centripetal, so no, it's v squared over r. And then I let the math take care of itself. So it's the same approach, it's just a different example of the same approach. Yes? Oh, I had them together. Oh, sorry, yeah. I'd like to say that's a deliberate mistake, but it's not. Thank you. So, and that gives me to the next point, actually, so what is the tension doing? If the thing was not going in circular motion, what would the thing be doing? Just hanging there, wouldn't it? What would be the tension in the string if there was no circular bit? It was just hanging there. What would the numerical value of the tension of the string be? 20. So if you think about it, that's your weight cancellation, and there's your centripetal acceleration payment. So it's doing two jobs. And if I take a merry-go-round, I used to ask questions about this, and I haven't done it in a long time, but I take not a merry-go-round, what's that called? A big wheel? The Ferris wheel? Ferris wheel, yeah. So if you think about the bottom, when you're going around the bottom, then that tension there is, well, you're going to have the same situation we have here. We're going to have basically, it's hard to describe it without some numbers, but I can say T minus Fg is equal to mv squared over r. And if I take that point there, then my mg is at 90 degrees. This is my mg. Can you see that okay? I worry about this thing being in the way all the time. I wish they could. It's as far away as I can take it. So if I do this, then my mg is at 90 degrees to my tension. So for this one, T is equal to mv squared over r. The tension's less because it's only taking care of centripetal acceleration. And up here, it's actually kind of even weirder because now my mg, my weight, is in the same direction as my T. So I would say minus T added to minus mg, if you like Fg, is equal to minus mv squared over r, because the acceleration is pointing downwards. So I get that T is equal to Fg minus, mv squared over r minus Fg. So in this bottom case, T is equal to mv squared over r plus Fg. So the tension is doing two bits. It's pulling the thing up and it's making it go in a circle. But at the top, part of the acceleration that's used for, part of the acceleration is paid for by the weight. So my tension is only doing, well, it's doing very much less. It's doing what I need for the centripetal acceleration minus my weight. So if I was swinging something around like a soap on a rope vertically, I'd have a bigger tension at the bottom than I would at the top. because the weight is adding to my job at the bottom, and the weight is doing part of my job at the top. But at sides, it's only centripetal acceleration. The weight is perpendicular, it doesn't matter. If you go get one of these Ferris wheels, it goes very slowly. It's probable that your tension is actually pushing upwards. So it's not really a tension, it's more like a thrust force upwards because it goes so slowly. But it wouldn't be, in going circularly, it wouldn't be as big a force going upwards as it would be if it was stood still. So quite involved situations. This next bit, don't want to get too far behind, so I'm just going to let you look at this over in your time if you want to. It will not be on the test. It's one of those kind of like spacey kind of things where it says, I can't put you in the room because you can feel. But if I videotaped a bowling ball in a truck, of an open-sided truck, I have a billiard ball hanging there, no air resistance, Billiard ball hangs there. If it drives by at constant velocity, the billiard ball is seen to be hanging vertically because there's no air resistance pushing it back. So the billiard ball on the end of a string, so the billiard ball will kind of hang vertically as it goes by. If I accelerate the truck, well, you can kind of see it, can't you? That's not a bad demonstration. That's it, constant. And then watch as I speed up. Can you see how it's left behind? Yeah. So, okay. Then there's an angle caused by the acceleration. If I don't videotape from the outside, if I videotape it from inside the truck, so you can't see the thing going faster and faster and faster. All you can see is the billiard ball and the string, the bowling ball and the string. And you see that. You have no idea if that's due to an acceleration in that direction, or it's due to some magnetic force, or some gravitational force. I mean, I could just turn on a magnet if it's a metal ball and it would do that. And when you're inside the truck, when you're working just based on what you see, you can't tell the difference. And that can lead to some problems. So the idea is, if I put you in a can and sent you into outer space and just accelerated you, you would think, maybe, that you were stood on Earth in a can, because you'd feel this weight downwards, and you'd assume it was due to gravity, but in fact it's because it's not a stationary can on a planet, it's a can which is accelerating at 9.8 meters per second squared in that direction. So if I put you in a can and accelerate you through deep space at 9.8 meters per second squared, there's nothing you can feel or tell that tells you between one and the other. Yet, there's no force there. It's an acceleration effect. And so, we call it a fictitious force. And the way we distinguish between a real force and a fictitious force is we think back about forces have two objects, and there's an action-reaction pair. And so you say, what object is doing this pulling? And if there's nothing behind the curtain, if there's not a planet or something, or a magnet or something, then, it's a fictitious force. I've got an acceleration. So it doesn't come up very often in day-to-day life because we don't tend to accelerate through deep space in everyday life, but it's there. So just if you're interested, it's there. It's just another example of using Newton's second law. Okay. So what I'm going to do is I'm going to stop there. I'm going to quickly go on to the